Okay, welcome back. This is now 3.1 on predicates and quantified statements. So 3.1 now, predicates, quantified statements. Okay. First, we begin with what the heck is a predicate. Predicate is basically just a variable, a statement that has a variable in it. So it's not technically a statement at first, but once you substitute in something for that variable, it becomes a statement. Okay, so I'll just write it's a variable statement. For example, a predicate, we'll call it P of X. So this is an example. P of X is X greater than 3. So something like this thing right here, we said before, it couldn't be a statement because X is variable, but we're going to call it a predicate, and then once you put in something for X, it'll either be true or false, so therefore it'll be a statement at that point. Okay. We want to work with these things. I mean, that's what you do in math. You work with variable expressions. We'll be looking for in the beginning the truth set for these things. So the values of X that make this thing true. So we have a truth set. We'll use set notation. If you don't know anything about set notation, chapter 1 has stuff on it. I'll try to fill in the gaps for you. This is the set of all X in some domain D such that P of X is true. Okay. So this weird backwards E symbol means in. This bar means such that. Okay. So again, this is a set of all X in D such that P of X works, or P of X is true. Okay. So for my example, the truth set would just be an interval. We have to know what domain we're working in. Let's just presume that we're working in the real numbers. So it's a set of all X in the real numbers such that basically X is greater than 3. What is that? Oh, that's just an interval, right? That's just the interval from 3 to infinity. Okay. This R that looks like this is the way you would write a boldface R. So if you look in the book, the real numbers are represented by a boldface R. In order to write that using my pen, I have to put like a bar right next to it, and that's what they do traditionally. Okay. So R is the real numbers. If you put a plus symbol up here, this is the positive real numbers. So the positive reals, which doesn't include 0. Okay, so 0 is neither positive or negative. So if you do need to include 0, you would, this book writes non-negative up in the exponent like that. So this is positive reals plus 0. Okay, which is, I never see that notation, but our book uses it. Other guys, the integers is Z, the rationals is Q, and then you could have positive integers by putting a little plus symbol up there, or write non-negative up there. Okay. Oh, okay. So I'll try to remind you of those facts as we go along if they're needed. Okay. So anyways, there's a predicate. Let's look at one of the problems in the book. This is number 3. Weird thing about number 3 is we have a predicate that's multivariable. You can have more variables in here than just one, right? So number 3 is going to be this. Let me find it here. The predicate is given by R of M comma N, and it means if M is a factor of n squared, then M is a factor of n. Okay. The domain here is the set of integers, so it's z. So they say note m comma n are both in, so there's my backwards e symbol, z. Okay. All right. So part A, explain why R of mn is false if m is 25 and n is 10. So here we have m is 25 and n is 10. Okay, so note if we plug that into this statement, if we plug these numbers into this statement, the first part will be true if m is a factor of n squared. So note that m is 25 and then n squared is 100. So 25 is a factor of 100. But then m is, it says it should follow that m is a factor of n, which is not true. 25 is not a factor of 10. Okay, so that does not work, and that's why it's not true. Let's look at part B. Give values different from part A for which r of mn is false. Okay, so you can kind of see maybe there's a pattern here. If this is 5 times 2, let's just do something times 2, right? So let's go 7 times 2, which is 14, and then let m equal 7 squared, right? So, and that's the form here. This is 5 times 2, this is 5 squared. So 7 times 2, and then 7 squared is 49. Okay, so we note that m is 49, and then n squared is, drum roll, 14 squared, 196. Okay, and 49 divides in the 196, right? So it's the way we've created this problem. On the other hand, though, 49 is definitely not a factor of 14. So this statement would be false in this particular, for these particular values of m and n in the integers. Okay, let's look at another part, I guess part C. Explain why r of mn is true if m equals 5 and n equals 10. So we have m equals 5 and n equals 10. Okay, so let's look at m and n squared. M is 5, n squared is 100. So in this case, 5 is a factor of 100, and also 5 is a factor of 10. So it works in that case. And then part D, they want you to pull the same stuff. They want you to do the same thing. Give values different from those in part C for which r of mn is true. So you basically just pull the same trick. We'll say let m equal some prime number 7, and then let n equal 7 times 2 is 14, right? So here m is 7, and then n squared is 196. 7 is a factor of 196, and 7 is also a factor of 14, so that's true. Okay, so this one was false, this one was false, this one was true, and this one was true. Okay, let's look at another one, probably number 5. They want you to find now the truth set of each predicate. So part A, the predicate is 6 divided by D is an integer. And D is in the integers. Okay. Okay, find the truth set. So all numbers that basically divide evenly into 6 such that those guys are integers. So I'm going to write it as in my set notation. And for this one, you'll just list out, I think one way to do it is just brute force list out the elements of that set. So the numbers that divide evenly into 6, that would be -6, -3, -2, -1, 1, 2, 3, and then 6. Right. There's other ways you could probably write it out. You could probably write, if you wish, the set of all, I guess, n in Z such that n is greater than or equal to -6, but then less than or equal to 6. well, you know, that wouldn't quite work, right? Because you would have 0 in this set. So you would have to adjust this and maybe say n greater than or equal to -6, but less than 0, and then n greater than 0, but less than or equal to 6. Okay, and because n is in the integers, you're not going to have like 1/2 and 3/3 and stuff like that. You'll just have the 1, 2, 3. Whoa, well, that ain't going to work either because you'll have 4 in there. Okay, so let's just scrap that whole idea. That was wishful thinking, and just leave it at this. Okay, well, there it is. All right, part B. The predicate now is 6 divided by d is an integer, but the domain is the positive integers. Okay? So again, the positive integers are just going to be the counting numbers excluding the negatives and zeros. So the positive integers is the set 1, 2, 3, ... means it goes on forever. Right. Okay, so now what is the truth set? The truth set is just going to be a simplified version of this, right? We just throw out the negatives and we have 1, 2, 3, 6. Okay, part C. Now the predicate is going to be the numbers x such that x squared is greater than or equal to 1, but less than or equal to 4. And here the domain x needs to be in the real numbers. Okay. Okay, so this time it's just going to be an interval, right? So you can draw a number line if that helps. So I need the numbers that are in between 1 and 4, and you can include these. But we have to have, so what's going to happen is we'll have these guys, but we'll also have, well, this is the result, right? So I need, sorry, I need the interval from -2 to -1. Okay, if I square any of those, it'll be in between here, 1 and 4. And I also need the interval from 1 to 2. Okay. All right, so I need to write that in an interval notation, I guess, and set notation. Let's put it in set notation, okay? At least try to this time. So the truth set here, it's all values x in the real numbers such that x is greater than or equal to -2, but then less than or equal to -1, or greater than or equal to 1, but less than or equal to 2. Okay. And you know, on a test, if you just wanted to write it in interval notation, I can read interval notation. So maybe you would rather write the interval from -2 to -1, and then unioned with 1 to 2. Okay, so anything in those two sets would work. Let's look at one more, part D. The predicate is the same as before, but now the domain is different. Okay, so the domain this time, we want values from the integers. Okay, so what would work in the integers? So -1 would work, and then -2 would work. So -2 squared is 4, so that would be in there. 3 won't work because that would jump out. Okay, but +2 and +1 would also work. So there's our truth set. You should write them in numerical order, but this works as well. Okay. Okay, so I think that's a good introduction then to predicates and truth sets and truth values. Let's now look at quantifiers. So quantifiers are going to allow us to work with predicates as if they were statements. Okay, so you'll have variables in there like this, but we'll slap on this quantifier, and it will turn this thing into a statement. Okay, so how does that work? Let's take a look. So this is section 2 now, the universal quantifier. Is first, and the symbol for this is the upside down A, and it means for all. Okay, so when you see that symbol, you say in your head for all. So some examples of statements with universal quantifiers: all human beings are mortal. Okay. So it's a variable statement. You don't know which human being they're talking about. But if you put a quantifier in front and you're saying all human beings, then all of a sudden it becomes a statement. That's either true or false. Right? We can, this will be the very informal way of writing a universal statement. But then we're going to turn this into symbols, right? So we can say for all human beings X, X is mortal. Okay, and we're going to make it more and more symbolic. And the hopes is, again, we could just plug all this junk into a computer and the computer can do the thinking for us, right? So we'll say for all X in H, X is mortal. And then you could probably go even further and maybe say for all X in H, and then just write the predicate M of X. Right? So M for mortal. Okay, so that's what we're dealing with. To prove that these guys are true or false is usually very hard because you'll have an infinite domain like the real numbers. There's an infinite number of things in there and you have to go through and check every one of them. That's not possible. So we have to develop some tools to be able to do that. And we'll have special types of proofs for proving these things. In the beginning, though, we'll mainly work with finite sets or things like that, so we can go through and test everything and see if it works. Okay, so first off, the truth or falsity of the universal. Okay, and I think this is an example from the book. She changes the book every semester, though, so I don't know. Let me look. 3.1. Yeah, I think it's still the same. This is example 3.1.3. Our domain is the set 1, 2, 3, 4, 5. The statement is for all x in D, x squared is greater than or equal to x. Okay, we want to know if that's true or false. And the way we can do it is just literally brute force it. Plug every one of these numbers, into this predicate and make sure it works, right? So we could check 1 is 1 squared greater than or equal to 1. Yeah, that's true. 1 is equal to 1. Is 2 squared, which equals 4, greater than or equal to 2. Yeah, that's true. Is 3 squared greater than, which is equal to 9, greater than or equal to 3. Yeah, that's true. And then finally, well, 2 more. 4 squared, which equals 16, is that greater than or equal to 4? And that's true. And then finally, 5 squared is equal to 25. Is that greater than or equal to 5? Yeah, that's true. So this is a true statement. Okay, so hence the statement holds, or the statement is true. Okay, all right. Let's look at one from the exercises. This is number 10. We have a universal statement and we want to prove it's not true. Okay, And the way you do this, the way you show that a universal statement is false, is to find a counterexample. All you got to do is find one instance where it doesn't work, and then that means it doesn't work for all whatevers, right? So in this case, number 10, the statement is for all a in the integers, a minus 1 divided by a is not an integer. Okay, so we need to find a counterexample, and so I'll say you want to find a number in the domain where this doesn't work. Okay, you only need one of them. So consider a equal to 1, and then we note if I plug 1 into the predicate here, I'll have 1 minus 1 all over 1, which is equal to 0 over 1, which is equal to 0, which is an integer. 0 is an integer. Okay. Hence, the statement is not true. The statement is false. Okay, so this is called a counterexample. Note the counterexample, and it's easy. It's an easy type of proof. You wish that all proofs could be that easy. Of course, they're not going to be. Okay. Okay. So that's basic functionality of the universal statements. Now we want to introduce the existential statements. Which existential exists, right? So 1, 2, 3, section 3 of my notes, the existential quantifier. We use the backwards letter E, and it means there exists. Okay. One note is when you use the for all symbol, you'll say for all x in whatever, and then you'll always have like a comma. Okay, for all x in R, P of x is true, right? With the existential, there exists an x in R. Instead of the comma, you generally put such that. Okay, but we know we have a symbol for such that, and that's just this bar. Okay, for there exists an x in R such that P of x is true. Okay, so that's just our symbol notation, general conventions. Okay, so anyways, more loose versions of existential quantified statements. There's a student. There is a student in my class. Okay, and then we can repetitively make it more and more symbolic. There exists a person P such that P is in my class. Okay, and then we make it more symbolic. There exists a person P in the set of all people such that P is in my class. Right? And then we could use the such that symbol and our predicate notation. There exists a person P in the set of all people such that P is in my class. So you could write it like that. Ain't that awesome? You get rid of the words, get rid of the human portion, and it's all just symbols. Right? Give it to a computer. The computer does the thinking for you because humans aren't good at thinking. All right. Okay, how do I prove these things are true and false? Again, we'll have other methods, hopefully later. Right now, our methods kind of depend on the fact that the set is finite, and we can go through and check every individual case, or we're just looking for one basic counterexample. Okay, so again, let me make sure this is still in the book. Example, I want 3.1.4. And it's still there, good. So example 3.1.4. Part A, we have the statement, there exists an m in the positive integers such that m squared equals m. Okay. So I want to prove that this is true. And all you need to do is find one example where it works, right? So can you think of that example? And you may have to fiddle around with it and do something. It's 1 though, right? So note or let m equal 1. Notice 1 is an element of the positive integers, so you have to make sure you're not using some element that's not in here, right? You can't use 0. So if you tried 0 and tried to use that as your evidence, it wouldn't work because 0 is not a positive integer. It's in the non-negative integers, or it's just in the integers. So you got to be careful there. Notice that. Also then, it fulfills the predicate here. Also, 1 squared is equal to 1, which is equal to m, which is 1. Okay. So hence the statement works. Hence the statement is true. Okay, but notice there are two things you kind of have to make sure. You have to make sure this is actually in the integer, the positive integers, and make sure that this statement is fulfilled. Okay. Part B, now we have a different domain. E, the set of integers 5, 6, 7, 8, and our existential statement, there exists an m in E such that m squared is equal to m. Okay? Okay, so you can literally go through and just try to find it or show that it doesn't exist. So notice 5 squared equals 25, but that does not equal 5, so that didn't work. 6 squared is 36, but that does not equal 6. 7 squared is 49, but that does not equal 7. And then finally, 8 squared is 64, but that does not equal 8. So there does not exist. It does not work. Okay? Hence, this is not true. And it's false. Okay? But again, the only reason why we're able to do this at this point is because the set was finite. We need different methods to handle infinite sets. All right. They'll be doing a lot of translations again, which is good if you're just reading a random math book. And generally, it's not going to be all symbols, right? At the beginning of the century, I think it was like Russell and Whitehead did the Principia Mathematica, where they actually turned all of the words into symbols and then tried to do that, let's crank out every theorem in the universe type idea. You could go back and try to get your hands on that. It's very hard because you have to kind of learn the way they do their symbols and everything. You probably need to know set theory a little better. But in general, in books, you're not going to open it up and just see long strings of symbols, right? You're going to have words in there, English words, at least in the undergraduate type universe. So anyways, we need to be able to translate from formal to informal. And okay, so some reference material, this upside down A, you could translate it as for all, for every, for each. The existential quantifier, there exists at least one for some. Okay. And then the ones that are confusing, at least in my opinion, that should never be used, but unfortunately are used, all are not. Okay. So you would write for all x in whatever domain, not p of x is basically what this thing is. But the way that it'll be written informally, people will say none are, or they'll say none ... are. Okay, it's this stuff which as soon as you see that, you try to translate it into this form, and then you can translate it into a universal statement. Right? But personally, I think these guys are kind of, again, I would never use that phrasing. It's annoying. Okay, so let's go ahead and dive in there and see some of the problems. Hopefully they're probably not going to be the same as what they are now. Let me look. Number 16. Sure. These are like fill in the blanks. That's the way it'll be online too. Rewrite each of the following statements in the form for all blank x, comma blank. Okay. So part A, or maybe we should just, sure, let's look at part A. All dinosaurs are extinct. Okay. So for all dinosaurs, x are extinct. Okay, it's not a big deal. You'll get the hang of it fairly quickly. Again, the hard part is when you get to these none are or no are statements. Oops, I should have written back here none are. This other one, no blanks are. Okay, sorry about that. So for example, I'm seeing it in the book, no irrational numbers are integers, part C. No irrational numbers are integers. Okay. So what I'm going to do with this thing is kind of turn it into an all or not statement. So for all for all irrational, or maybe just all irrational numbers are not integers. Something like that. All irrational numbers are not integers. So I kind of translate it from here to here, and then I'll put it into this form. Right? So for all irrational numbers x, x are not integers. Okay, that's kind of clear. I don't know. Let's do an existential one. So if you need more work, go into the book and do the blue exercises. Okay. So let's look at 17. So 17 wants you to rewrite each of the statements in the form there exists a blank x such that blank. Okay. All right, so part A, it says some hatters are mad. Sorry, some exercises have answers. Okay, so I would say there exists an exercise X such that, and a lot of times teachers will abbreviate such that as ST, such that X have answers. Okay. Okay, so it just takes a little bit of practice, so no big deal. Let's move on to now combining, the universal conditional and the existential and. Okay. So what you're going to see here is now more complicated predicates. So you'll see if-then statements, and you'll also see and statements. You'll also see sometimes or statements. Okay, so section 5 in my notes now, we're looking at universal conditionals and the existential and. Okay, so the universal conditional, how that go? It'll go for all x in whatever domain. If some predicate is true, p of x, then it'll follow that some other predicate is true, q of x. Right? The existential version, now existential and, there exists an x in some domain such that p of x is true and q of x is true. Right? And then we're going to want to be able to negate these things. And I was saying earlier in the semester, we're going to know how we have to know how to deal with these if p then q statements and how to negate those. So remember, how do I negate this? Well, if you don't get the work on time, then you're fired is equivalent to saying either you get to work on time or you're fired, right? And then we want to negate these, right? So the negation of if p then q will be equivalent to the negation of not p or q, which will then be equivalent to p and not q. Okay, so we're going to need that here in a bit. I just want to remind you of that fact. Hopefully you have that kind of encoded in your hard coding somewhere. All right. So anyways, first we're going to start with some translations. So 23. I hope it's still 23. Let me look. Okay, yeah, we're good. So 23, they want you to rewrite it as a universal if-then in two ways. For all x, if blank, then blank. And then the other way is for all blank x, blank. Right? So you could basically take the universal statements we were looking at earlier and kind of turn them into if-then statements, where the if part is usually the domain. So for all real numbers x, x is divisible by 2. Okay, so over here, for all x, if x is a real number, then x is divisible by 2. So you can kind of play that game. Anyways, let's see what they have in the book. Part A, all equilateral triangles are isosceles. Okay, so for the first case, I'll say for all x, if x is equilateral, then x is isosceles. Okay? And then likewise, how else can I write it? For all equilateral triangles X, X is isosceles. Okay. What else? Let's do an existential version now. So this is, at least it used to be 24, and we're going to play the same game. We're going to rewrite an existential statement in two different forms. There exists a blank X such that blank. And the other form, there exists an X such that blank and blank. Okay. Sorry, I went off the screen now. Okay, so what is the statement? The statement A is some hatters are mad. Just a side note, Alice in Wonderland, I think, whatever that book was, the guy that wrote it was hardcore into logic and things like that. So that's probably a good book to read on the side if you're got a lot of extra time on your hands with the pandemic and stuff. All kinds of cool logical things that you could look into. There's the Tarski stuff that's in the book. I'll try to put that in my notes. That stuff's really cool too. So anyways, some hatters are mad, the Mad Hatter, right? Let's think about how we can rewrite it. So there exists a hatter X such that X is mad, right? There exists a hatter X such that X is mad or insane. And then you can also rewrite it as there exists an X such that X is a hatter and X is mad. Okay. All right. Let's see what else we got. Oh yeah. So there, usually when you're dealing in like pre-algebra or pre-calculus, those classes, we don't ever really specify domains. We just kind of assume. Especially in calculus, if you've taken calculus, you'll know you never ever work with complex numbers, and we never say it out loud, but it's kind of implicitly implied, right? So you can kind of leave out the domain, but if you leave out the domain, you have to change the notation a little bit. Okay, so implicit quantification. So for example, the universal statement for all x in the real numbers, if x is greater than 2, then x squared is greater than 4. Okay. You can kind of leave out that first part, but if you leave out the first part, you have to change this arrow to a double arrow. Okay, so it'll look like this. X greater than 2 implies x squared is greater than 4. Okay, so not a big deal. It's just kind of a notational thing. Let's look at maybe one of the problems in the book associated with that, number 33. Okay. So the domain in this case is given as the real numbers, and then you got to determine if the statements are true or false in the real numbers. Okay, so part A is greater than 0 and B is greater than 0. Does that imply A times B is greater than 0? So I'm not talking, I sort of have defined the domain up here, but in this I have not talked about the domain, so I use a double-headed arrow to implicitly say that we all know what I'm talking about. I'm talking about the real numbers. So in general, is this true? And just by thinking about it, I would say it's true. I don't have the mechanics to actually prove it in a nice formal programmable proof, but yeah, it seems like that goes without saying, right? Well, no, it doesn't. There's counterexamples. No, it does. So if A and B are both positive, A times B is also positive. So you could write it out like that. You could say, for all A and B such that A is greater than 0 and B is greater than 0, we note just from our knowledge of positive times a positive is a positive, right? We note A times B is a positive times a positive, and therefore a positive. Okay, and so A times B is greater than 0 because that's the definition of being positive, right? Thus, A times B is greater than 0 by definition, positivity. Okay, so sometimes proof classes, if you keep taking those, will get kind of annoying because you don't know what you can assume and what you can't assume. But usually your teacher will give you, okay, these are the ground rules, buddy, and you got to kind of work from those ground rules to prove anything. So sometimes in the book it will get a bit taxing because these are truthisms that you've kind of embedded in your brain from childhood. Right. This sort of thing you would never imagine having to prove, right? But the truth is somebody somewhere along the line proved this stuff. And they prove it in set theory, axiomatic set theory. I'm sure they do it there. Okay. Anyway, yeah, let's leave it at that. And no, let's do a Tarski's World thing. So these are really cool. And you can, at least back in my day, you could buy this program that would give you kind of logic puzzles, and it would be like a chessboard. Okay? So you'd have this big chessboard type deal, and these guys wrote a whole book on it. I had the book, but I just never got around to learning their language and stuff. So there's 1, 2, 3, 4, 5 columns. But you can buy the software online for like $10 and then play around with it. And what it does is it kind of auto-generates puzzles like this. And then you have to decide whether or not the universal or existential statements made about the puzzle board are true or false. Okay, so it's kind of neat. I don't know. Anyways, it'll be populated with geometric figures and colored. I don't have colors, so I'm just going to put like little indices to represent the colors. So 1 is equal to blue. 2 I'll say is black. Okay. And then 3 I'll say is gray. So here this is a blue triangle and its name is A. All right. Okay. And then we have a black, a circle, its name is B, and its color is black. And then I have a triangle here, its color is blue, I'll call it C. Then a circle here, it's gray. And then I have a square, it is blue. And then I have a circle, which is gray. And then I have a triangle, it is blue. Then I have the square, which is black. Then I have a circle, which is gray. And then I have a square down here, which is black. And then I have a circle over here, which is gray. Okay. And then I make you can make statements about this. see which one is true, which one's false, etc. So it's 27, part A. For all objects U, if the object is a circle, and we use kind of this predicate notation. So this means object U is a circle. Then the object U is gray. Okay, you got to determine if that's true or false. Okay, so basically for all circles, they have to be gray. So you go back and look at all the circles. Circle B is black. So no, this is not true. It's false because circle B is black. Okay. Let's look at another one. B. There exists object Y such that Y is a square and Y is above object D. Okay. So we have to find a square that's above D. So where is D? D is here, and there are certainly no squares above it. So this is false. Okay, and it basically teaches you that to kind of think in terms of these this new language, and which could be very valuable if you're working with a lot of math. Like I said, there's always this issue of we have to kind of teach math in English, but I think math is better suited for just symbols. You know, collecting ideas, arranging them, and making logical conclusions based off of the ideas. So sometimes it's very helpful to be able to translate all that English into just the bare bones symbols, collect those symbols, and then make your conclusions from there. Makes it easier to follow some math arguments as well. Okay, we'll leave it at that, and we'll see you next time. Bye.